Hi everyone. My name is Rakesh. I'm from the ULIS Supercomputing Center, and today I'm going to talk about predicting turbulent boundary layer flows using transformers coupled to the multi-physics simulation tool m-AIA. So this work is in collaboration with our partners at Aachen University, and let's go ahead. So to start with some motivation, so what are we trying to do here? So this is what we are investigating is an active drag reduction technique where we are, as it says, trying to reduce the drag. And this is an animation of flow over wing section. And as you can see, we introduce these transversal surface waves in the spanwise direction, which results in a reduction of drag. So on this inset line plot here, you see the black line, which is for the non-actuated case, the drag in the non-actuated case, while when we introduce these spanwise surface waves, we are able to reduce this drag. So of course, since we are reducing the drag here, so the motivation is to reduce emissions, right? So this, in the long term, we would like to, this inherently leads to achieving the climate and sustainability goals. And in the short term, we are interested in learning more about different, we are investigating in this in different directions. So from the Aachen side, they are looking at understanding the mechanism behind this reduction in drag. So looking at this more from the fundamental side, and also, for instance, optimizing the design choices using Bayesian optimization techniques, for instance. While in this talk, we are focused on reducing the simulation costs. So we are trying to use a machine learning technique, specifically with transformers, to reduce the simulation cost of this high fidelity solver. And long-term vision is, of course, application in airplanes, high-speed trains, things like that. Okay, so we have the problem now, right? So we said, of course, the long-term objective is to apply this for airfoils, and what we have is sort of a dual optimization problem here. So we are, first of all, trying to maximize the drag reduction. So delta CD is the drag reduction which we achieve for, let's say, a certain set of actuation parameters. And the other objective is to also maximize the net power saving. So you might understand that introduction of this wave into this wing involves injection of energy. So we would also we would not want to spend more energy than what we gain. So the other optimization parameter here is the delta P net, which you see here. So these are the two parameters we are trying to maximize. And these are the set of actuation parameters which basically define the wave. So these are the wavelength, time period, and amplitude of this wave. And for the chosen actuation parameters, we would like to maximize the drag and net power saving. So that's the definition. And then we generated some training data for different combinations of these actuation parameters. So this is the computational domain. We have the inflow here. So that's the the important point is that we, of course, this is still an academic case. So we simplified the problem to a flat plate boundary layer, turbulent boundary layer, where we introduce the wave on the wall at the bottom here, and that the inflow direction and periodic boundary conditions on both the spanwise directions. And this is basically the equation, how the wave is defined. And the training data for the transformer that we train later is generated with the well-resolved large eddy simulation. These are the resolutions in the three directions, X, Y, and Z. And we have a second order accurate Navier-Stokes finite volume-based discretization with a body-fitted deformable structural mesh, and the time integration is with the 5-stage Runge-Kutta scheme of second-order accuracy. And for the transformer model itself, we required a higher resolved transient simulation. So we had to run a new set of simulations, and these are the configurations for which the new simulations were run. Now let's come to the challenges. So yeah, of course, as you might understand, this is high fidelity LES simulation. So on the solver side, these time integrations are expensive. Yeah, even if we use massively parallel resources. On the machine learning side, of course, there are yeah, I mean, quite a lot of techniques which are used, which could be used for solving transient problems or dynamic problems. And for instance, recurrent neural networks, for instance, have been used for quite some time, and we have issues there. But in the last few years, all of us know that there are these transformer models specifically used extensively in the natural language processing community, which promises quite a lot. So this talk is targeted towards using one of these transformer models for solving this problem or accelerating the problem, I should say. And the third challenge is on the coupling side. Yeah, so here, as I said, we are trying to accelerate, not really replace the solver. So we would also need some sort of coupling between the solver and the machine learning model. And many legacy solvers, CFD solvers, are still CPU based, although a lot of them are being ported now to GPU. But we have, for a lot of solvers, this problem of them being CPU based, while ML training, as we know, benefits from GPU acceleration. So we need some sort of coupling there. So that is another challenge we try to address in this research. And so how the workflow looks like. So first we train the transformer model, which is generated with m-AIA based actuated turbulent boundary layer dataset. So m-AIA is the flow solver, which was developed at the Institute of Aerodynamics at Aachen University. The next step is then to couple m-AIA to the transformer model. So once we have this trained transformer model, we would like to couple them. And then we would like to offload, let's say, a few time marching steps to the transformer inference engine. So out of this, the coupling step is still ongoing. So we still face some challenges there. But today we are going to look at the results of the transformer itself and also the speed up that we achieved. So the final objective is then to speed up the time marching of these TBL fields, where we have the m-AIA solver on one side. AI for HPC is the framework we developed, which does machine learning on high performance computing systems, which was developed under this project zero-erase. And then we have the Fidel in between. So Fidel is basically the coupler, which helps us to achieve this coupling between the physical and the deep learning fields. So to look at the architecture, so we adopted an architecture which was initially used for a dynamic problem. And there we have an encoder-decoder configuration where on the encoder part, there are 6 layers for the encoder. Initially, there is an input layer and a positional encoding. And each of these encoder layers have, as you know, self-attention and feed-forward layers followed by normalization. And similarly, it also looks similar for the decoder, except here we also need the encoder-decoder attention, which basically is this arrow that you see here. And then for the decoder, we also need to apply this look-ahead mask so that the network does not see information from the future when it's predicting something. And we also did some hyperparameter optimization to arrive at this number. So in terms of the number of layers, attention heads, and things like that. And then the other challenge for us is also the non-uniform input. So if you saw the problem initially, we have these different sizes of boxes which arise from these different parameters of the equation, which results in non-uniform samples for the input to the transformer network. So we do some sort of reshaping to smaller cubes, which allows us to tackle any input shape, and also it reduces the complexity of the attention mechanism. Yeah, these are some training parameters. So Atom Optimizer, we use the deep speed framework here, which is provided by AI for HPC. And then, so from I also told before that we have a highly sample data set for this particular use case. So this was basically done. So we save the sample every 24 physical CFD solver time steps. So a transformer time step would then be defined by 24 times the delta T of the CFD case. And so to give you an idea of the convective time here, so the transformer time step would be approximately 8% of the boundary layer thickness that you have. And the loss, we have loss here behind the inset here is defined by the mean squared error and the gradient loss. So these are some qualitative results. So here you see these 2D plots, which are plotted on a plane parallel to the wall. So you see the wall here. And these are for different values of delta TR. So that's the transformer time step I was talking about. So as you can see, as we increase the delta TR, our predictions become worse. So here you see already quite some discrepancy, while for lower values of delta TR, we are still at a relatively good agreement. We also looked into the statistics. So we use the dynamic mode decomposition method to look into the reconstructed modes from the LES field and the ones reconstructed by the transformer model. And we see here also good agreement qualitatively in terms of quantitative quantities. We looked at, let's say, the relative Frobenius norm between the nodes, for instance. And what we see here in this table is that below delta T TR, so the transformer time step of less than equal to 5, we have a relative error of about 3%, which is quite good for this particular case. But of course, we should be careful in terms of for how many steps we are using the transformer model. So because after a certain time, the errors start creeping up. So the next step, of course, is to look at the gain. Yeah, so what do we really gain anything by bringing in the transformer model here? So here we do a comparison of the inference time, which we gain, which we have on the transformer model, and then comparing it to the time stepping time integration time from the m-AIA code, so which is the LES solver, which is mentioned. And yeah, this comparison is of course not so straightforward in the sense that the inference is done on GPUs. So here in this case, A100 GPUs, while the LES code it exploits CPUs on the Hawk system, although both the CPUs are same. And then we compare statistics, let's say for a single time step. So these are the numbers that we obtain, let's say for a single time step of the transformer model. So in terms of wall time, we have a significant gain of about 53x when we compare both, while in terms of memory, it's even more higher. So the summary is that even if we use this model for a single time step, we already gain significantly in terms of both wall time and memory. So the next step is to couple the solver to the transformer model to the solver, and this is something which is done with this framework called FIDEL. So this is this coupling framework developed by our collaborators at Fairfax in the COE race project. And here, FIDEL already offers a lot of interfaces, Fortran, C, Python, and it works via, the mechanism works via a m-AIA based paradigm, which uses the multiple data paradigm. It establishes a mapping between the two, let's say, processes running on the physical and the DL side. As I said, there are already these different interfaces available. And in our case, the DL engine is the Python script, which does the inference of the transformer model. And to show you a bit of a flow chart of how this looks like, So we have the finite volume structured solver, which is basically the m-AIA solver that we have, which sends the velocity fields to this ML coupler Fidel. And this ML coupler then sends these velocity fields to the DL engine. So these are m-AIA send and receive commands, which are done. And then the DL engine itself, it does a few steps. So these are the steps which are done within the transformer inference code. There are these different classes which are performed. So basically, extract cubes is the one I showed before, where we break up the larger cube into smaller subcubes. And there is the inference one, and then combine is basically to reconstruct the entire larger cube back. And then there is another send and receive command, which happens here. So that is the workflow. Yeah, that's the same thing I already told you. Now, yeah, but this is still work in progress for us. So yeah, we have an idea of how this will go ahead, but this is not yet implemented. So that brings me to the conclusion. So we showed the transformer architecture to exploit and exploited it for time marching velocity fields in a turbulent boundary layer flow problem. We analyzed the fields, predicted fields with the dynamic mode decomposition method, and we were able to achieve an error of less than or equal to 5% for horizon of 5 future time steps. Significant computational savings were achieved, as you saw. So the idea here is, of course, to accelerate rather than to replace, which does not seem feasible at this point, at least, to offload by offloading a few time steps. So even as you saw, even with a single time step, we are able to achieve these kind of numbers. And yeah, then the coupling is behind here. Coupling is ongoing, but already at an advanced stage. The important thing to consider once this coupling is achieved is to quantify the mass and momentum imbalances, because that's where the convergence might be difficult for the CFD solver. Yeah, with that, I am ending my talk, and I leave some resources here. So yeah, that's the CFD solver. m-AIA is now open source. So these are some links if you are interested. Yeah, and thank you.